All right, welcome in everyone. We're going to we're going to start off where we left off last time, which is looking at collisions in two dimensions. Last time we examined two types of collisions. There was elastic and inelastic. One of them, the objects in the collision bounce off of each other. And the other one, they stick together and sort of form one large unified mass. It's the exact same sort of principles in collisions in two dimensions, except we now are going to be sort of looking at objects and sort of listing out their vertical momentum, their vertical kinetic energy, if it's sort of appropriate, and also their horizontal momentum and horizontal kinetic energy. So here we have, I don't know if everyone got to see last time, so I'm going to show it again. We have this air track over here on the side, and we have two cars. And I'm going to arrange them in a way that they will elastically collide with one another. So they are going to bounce off. Momentum is going to be conserved. And in an elastic collision, the kinetic energy will also be conserved. So this air track sort of provides a frictionless surface, like an air hockey table. And this one thing by itself, it will probably go forever, provided nothing bad seriously happens. So this is what I've sort of always meant when I say something frictionless. The object is not technically grinding on. It's not sort of like slowing down from a surface. It is going to, once you give it a push, going to go. Frictionless. Now, on this frictionless surface, I'm going to have an elastic collision. So, two objects sort of coming towards each other, they change directions. Remember last time I said momentum was a vector? So, the direction is important. And I can show that a bit more detail with sort of an experiment like this. One object stays still, and they're not exactly the same mass. That's something else we have to keep in mind. So let's say this object stays still, and I send it another object towards it. The momentum of the system is conserved. The total amount stays the same. Alright? I could also, find velocities. I could also look at kinetic energy. The kinetic energy is also conserved. Now, this one. Let's look at an inelastic collision. This is something where they're going to stick together and they're going to form one big mass as they move after the collision. Let's say one of them stays still, and one of them comes together. After the collision, for this case, momentum is conserved, but kinetic energy is not. That's sort of a big thing to remember there. Let's look at, I didn't do this last time. Let's look at something where we have something significantly heavier, significantly more massive, sort of colliding with a smaller object. I'm not going to do it too hard. That's 580. This is about 200. So this is about almost 3 times more massive than that object. So what's that? So this one's going to stay still. Let's see what happens. I'm going to do it too quick. So in this case, this sort of initial projectile, you can call it, kept moving forward. In the other example, since they were approximately the same, the projectile stayed where it was. Do that one more time. All right. What if we have a inelastic collision, something a bit more less significant? Because it's trying to move, imagine like you're trying to move a mountain. This is one small thing running into another thing. The momentum is always going to be conserved, but it's not as showy in this case. All right. So that was our sort of linear example. This thing's moving left and right. Very easy to tell direction. Things moving to the that way, to the left, I can just say are negative. And when we move to something in 2 dimensions, we have to bring in that same sort of rules we were using before. Things moving up is positive. Things that move to the right are positive. So let me just do a quick little up and to the right are positive. And eventually, you can see with this, it could be like any sort of collision. It could be, I could look at like cars, sort of running into each other. This car going like that, this car going like that. This is a top view of maybe like an intersection. Or maybe we have something, projectiles, 2 things that are colliding. This is, I think I should have brought this out in the beginning of the chapter, but it's also still pretty fun. Let's go like this, and you move the table. We have basketball that's much heavier, much more massive than the tennis ball. And these 2 things are going to collide with one another. But the total momentum of this system is going to be conserved. And so what we see happening, this is not like a fully inflated, it's just like kind of flat. And we have a regular tennis ball. But when we have this collision of these 2 objects with different masses, moving with now a matched velocity, the momentum will remain the same, and you'll see what will happen. So go like that. If this was a fully, or like a regular basketball, the tennis ball would go like up to the ceiling. So I guess it's not, the safest thing. If I'm having it right here, this is the danger zone. But we have this sort of little example of conservation of momentum that you could see with some collisions. All right, we have this top-down view. It could be any sort of thing, projectiles, anything colliding. We just need to say, or we need to classify. We'll say like horizontal. We need to compare the momentum before and after. We do the horizontal case, and then we also need to remember to do the same exact thing except for the vertical case. So I've just put horizontal and vertical over. I could just also say like x is this x, y, y. And remember, these are all vectors. because direction's important. Okay. And that goes for, summing the total amount before and after. All right. That leads into a pretty good example that we'll get through. We have two test cars that are going to collide. Car 1 has a mass of 1,700 kilograms. It's moving with a velocity of 40 meters per second east. That's east. Okay, so we have, let me put a little compass. Okay. I will just call it mass 1, velocity 1. And car 2 has a mass of 3,000 kilograms, is moving with a velocity of 20 meters per second. And it says right here, exactly northwest. So this is going to be sort of this 45-degree angle right in between these two. Right there. So we have this car, 45 degrees kind of going that way. V2, M2. Awesome. So the collision that they have, the type of collision they have, is perfectly inelastic. So that means they stick together and sort of become one big car, sort of smashed car after this collision. By the way, 40 meters per second, that's about 100 miles an hour. So we have this, very energetic impact between these two cars. What is the velocity of car 1 right after the collision? So we have these two cars. One of them's going completely horizontal. One of them's going kind of at an angle. So we need to find what is the horizontal component of car 2. Okay, if you thought you were getting away from vectors, you are mistaken. So we have velocity 2, velocity 2x, velocity 2y. And since it's 45 degrees, I could just say that's the angle right here that I'm measuring from. Okay. V2x is V2 cosine of the angle. And V2y is V2 sine of the angle. All right. So, cosine of 45 degrees, and we have 20 times sine of 45 degrees, 20 . So I have not done this beforehand. Okay, 14.14, and that's going to be the same for both of them. Awesome. So we have the components of the velocity. Yeah.
Just a quick question. How do you calculate the 45-degree angle?
45-degree angle. So this is sort of the word trickery that's going on here. We have up in the problem it says exactly northwest. So look at this little compass right here. So that means exactly right in the middle between north and west. So it's typically what will be a 45-degree angle.
Okay.
Yeah.
I know you can use 45, but can you use like the larger angle?
You can, yeah. It's just making sure you remember that it's at the very end. You can call left negative and down negative. Right, so that actually brings a good point. That means that my x velocity is negative. There we go. Because it's to the left, it's positive y because it's going up. All right. So now we can do the, horizontal momentum and look to see what we have. Horizontal. So initial is going to be 1. P1 final plus P2 final. All right. So in the horizontal case for the first car, we have mass 1, 1700 times its velocity, 40. Then we have to add the initial for that second car, which is to the left. But it weighs a lot more. It's 3,000 kilograms. So this is like a truck. And a negative 14.14. And that will equal, I'm running out of room already. That will equal, I think it'll be easier if I just do the calculation right now. Two, 3 minus, this is going to be bigger, possibly. No. Okay. So that is 25580. So that's just the initial side. Let me see how I can do this without erasing too much.
Question?
Yeah.
Why is it negative 14 and 14 and not 20? Aren't you multiplying the mass and the velocity?
Right, yeah. So we're just looking at the horizontal component of velocity right at this moment.
Okay.
Right? So we're just looking at this velocity right here because it's moving to the left.
Okay.
Okay?
Professor?
Yeah.
So why did you look at velocity 2 instead of velocity 1?
Velocity 2 instead of velocity 1?
Yeah, so we have mass 1 and velocity 1.
Mm-hmm.
Why did you decide to create a triangle out of velocity 2 and not velocity 1?
Okay, if I make a triangle out of that first one, where would the height of the triangle come from? Remember, we're always going to be looking at something on an axis like this. Right, and so what we have is velocity 1 is moving completely horizontally. So there is only a horizontal component with that first mass. You get that kind of?
Okay. Yeah, I see it. Okay. Thank you.
Okay. All right. Two, 5, 5, 8, 0 is equal to, this is going to be a inelastic collision, perfectly inelastic, so they're going to be stuck together and moving with their own sort of new third velocity. So we're going to see something like this, m1 plus m2. If I had more space, I would sort of elaborate a little bit more. This is something that we saw last time, right here. So we have this initial case, I'll put it on the board. So we have this initial case of these two things coming together. V1 plus M1, but they're stuck together this time. They're both moving with the same velocity. And that is something that I've written like this. Oops, sorry. 1, 2, 3. That's only for an inelastic collision. When they're after the collision, they're sort of moving together. All right, and we have. Oops. Come on. This is going to be 2.5 divided by so I have to remember this is only for the x direction. Five, 8, 0 for 700 kilograms. All right, that shows us that we have an x component of that new sort of combined velocity that is, I'm going to stop turning off, 5.4 meters per second. And so what I've done here is only for the horizontal component for this sort of path. I can keep going for the vertical component, but it's more of the same sort of thing that we've kind of been doing already, adding forces. Look at just the horizontal, sum those up. Then we're going to look at just the vertical, sum those up. Yeah.
I was going to say, how did you get 5.44 meters per second?
5.44. So I'm solving for this.
Oh.
Right, so right. Oh no, what did I do? So right here, I've just added the mass in right here, and I've divided this 4,700 to the other side to get this new velocity. And it's positive, so that means it's going to be moving to the right. I feel that maybe some people have got it. I don't want to spend, it'd probably be 5 or 10 more minutes on this example. If you guys want to see the second half to this, you can stick around. But I was also, for a sidebar, after about half an hour or so, I'll end the class and I'll pass out your quizzes, and I could go over the quiz also. So a lot of things we could do after class today. All right. So with that, we have sort of, yeah.
Just for that example, really quick, you can cancel or make at least the initial for the M1, or not M1, but B10, since there's no Y.
B1, yes,
Okay.
yes,
Yeah.
right. That'd make it like a bit easier. I already had no room. Right, so it's only moving horizontally, so there is no vertical momentum for that case. It would just be all from that second mass moving. All right, so we are on to a new chapter, rotational motion, and they sort of added gravitation in there. I don't know if I want to keep that in. Maybe not. But let's start talking about rotational motion. So things that we've been looking at so far, things like this air track, things like, I had just me in a chair last time, things pushing forces in a straight line, left, right. That's all linear motion. We've done kinematics and forces, all just on things that are moving in space. So, me tossing the ball, tracking where the ball is in space, like left, right, up, down. Now let's see what happens when things might do something else. There's other types of movement. There is rotation. That's when an object, other ways, yeah. In the real world, things just don't, I don't see this ball or like a wheel just sort of gliding on the ground too often. Things will have to rotate. We need to know how can we predict and sort of comprehend the types of forces or motion that's happening here. So we need to examine some rotational motion. We can start by looking at rotating objects, sort of solid bodies. This wheel, a good example. I have that thing, we'll get to in a minute. A ball, I can't really spin it on my finger that well. Tossing a football through the air, it has sort of a spin to it. Things that spin, or I should say solid objects that spin around a fixed axis. That's a technical sort of phrase. Things like that will be rotating around the axis of rotation. So I have a few examples up there. Sort of like this bicycle wheel. I think I've been on one like that. It's pretty fun. For any sort of rotating thing, it will always have an axis of rotation. Where is all of the stuff spinning around? In this case, the axis is this metal bar pointing towards you guys. So I just let that go for a while. If I was to flip up the bicycle wheel, now the axis is pointed up. It's that dotted line. In most of these cases, it's vertical. The axis of rotation is vertical. Even for people and objects, not necessarily round objects, they also have an axis of rotation. I would say in the case with the top and the amusement park ride, the axis of rotation is kind of swaying a bit, sort of precessing a little bit. That's kind of giving it this sort of fun tilt. So we've been looking at linear motion. And in linear motion, we saw a few ways to describe position, velocity, and then acceleration. That's kind of where I started the semester. I was like, here's a ball. How do I tell where the ball is? I need to find a way to measure its position or its displacement. Okay? How can I do that with things that rotate? Same sort of thing. Where is, not the ball, but something like this.
Yes.
Think of like this red dot on this bicycle wheel. So where is it in time as this starts to spin? And then I stop it. How far did it go? How much did it rotate? These are things that we can look at. I was going to add pictures, but I figured I'll just have a bunch of sort of spinning things. So in this case, like a car that moves or something, it has this displacement that I called delta x. That's change in position. And then we had something looking at just the velocity. That was what we started learning about vectors. And then, in the linear sense, the change in velocity. How is the velocity now different than the velocity before? Initial, final. That was what we called acceleration. Same sort of setup, same premise, but with things that rotate. So starting out, see if that will stay. There, typically we will always start measuring an object's sort of angular position, angular displacement from sort of the right side of the grid. This is commonly, I'd see like 0 degrees or 0 pi or something like that in radians. That is position, and we can measure where something's position is as it starts to rotate. This will be called angular displacement. I don't want to do like a really bad small picture right here, so I'll save it for the next slide. But I'll at least put these symbols up. So we have displacement in place of linear displacement. This is angular displacement. We have angular velocity, which is this Greek sort of W. That's omega. So lowercase omega. And we have the angular acceleration. That is this, it's alpha. Angular velocity. angular acceleration. All right. I'll explain a bit more on the next slides. All right, angular displacement, that sort of delta theta thing I put up a while ago. So that's related to finding the objects. This thing just spins on its own. Finding the position of a point just anywhere on a circle. It could be this red dot on this bicycle wheel. It could be, halfway in. It could be anywhere on the spokes. Tracking this object as it moves around in a circular motion. That is angular displacement. So all points on a rotating object. Sticker kind of, I don't know. So all points, out here on this wheel, halfway, a little bit in farther, maybe right next to the axle. All objects, expanding out, have the same angular displacement. I have a few pictures that will help a bit. So we have angular displacement is related to the radius of whatever type of circle or arc you're making, and that's a radius, and the arc length of however far this thing's moving. So that is, we're going to call that S over R. So this is arc length. And radius. All right, so simply I could do see where this thing is now. Always moving, okay. See where it is now. In a moment's time, I could see where it is at this point. How far did it move? That's going to be the sort of displacement part. How far did it move? How far was it displaced? That is delta theta, like that, which is just basically final minus initial. I guess I should also put that it has it right there. The units for this angular displacement is just radians, or I'll commonly just put rad. Okay. All right. This is kind of showing. I don't know how much I like this for the physical example. This is pretty much that graph right there. This is a real thing. So we have a circle that is radius of about 12 inches, right? Radius of 12 inches, and we found the radius. If we find the arc length, that's the outside edge. That's where I'm measuring from. I want to know this point right here. So if we find the arc length, we go like this on the edge, and then measure it. That is also 12 inches, like that. So this has an equal radius and arc length. That means that's 1 radian. I can do this for anywhere. So I could do something like right here. I can find that radius, and I can find that sort of arc length, and it will be the same thing. It will be 1 radian. And that's why I only need to know kind of where the angle of this thing is. I don't really need to know how much the wheel has spun. So let's see. 1 radian is about 57 degrees, kind of like right there. What if I sort of just keep spinning this thing and I let the timer go? Go, go, go. Then I stop. So that same point has gone around and around and around and around. And typically we just like restart. We go 360 degrees and then start over again. But in terms of radians, right here, I would just keep adding them up. So I can make this like go for a really long time. I can say this thing has traveled so much distance, so many sort of like a span of angles. It's gone 100 radians, or whatever. It's spun for a long time. So that's when I talk about angular displacements. How much has this thing been turning? That kind of makes sense. Then we could talk about angular velocity. So where the thing is, once we get that down, angular velocity is the exact same thing as linear velocity. That's right. So once we understood position and displacements for things moving in the lines, we're able to say, okay, once it moves this amount in this much time, we can find the velocity. So that's the same exact thing for angular velocity. We can find the average. Sounds like it's too loud. Okay. Which is basically just the change in angle. Oops, sorry. Over the change in time. All right, and we're back to this. That's sort of the formal. What if I want to know the velocity right at a specific moment? That's the instantaneous velocity. So the formal way, limit as time goes to 0. Oops, sorry. There we go. Typically, you will just be finding kind of, average velocities here and there. Hopefully, all of this is kind of just real familiar from that, first couple of weeks we were having, where I was just going over, here's position, here's velocity. It's the same exact thing. Now things are spinning. You can also find angular acceleration is how the angular velocity is changing. Okay. So it's just basically velocity when we started, velocity when we stopped. So it's some sort of change in velocity for a period of time. Okay. And here's this. This is really just sort of to cover just in case you have an instantaneous acceleration problem. I should make this more clear. Limit t goes to 0. All right. So, same exact thing, just slightly different symbols. That leads us to being able to track how an object moves. Remember last time, or I guess a month or two ago, when we were going over things that move, we were able to form some kinematic equations of motion. So like a list of about 4 equations that show us how things will always move in a line. We can do a similar thing for rotating objects. And the condition for that linear case, how we were able to get those 4 equations, was there had to be a constant acceleration. So if we have a constant acceleration that is continuously, let's set that slow, continuously changing the velocity somehow in a constant way, we are able to make some rotational kinematic equations. So this sort of basic example I have here is, the wheel at one moment will have an initial rotational velocity that way. And then after I accelerate it a little bit, for a small amount of time, it will have a difference. Velocity. So we have that plus however long I was accelerating it. So that leads us to like the same exact type of first equation from our list of kinematic equations. So yeah.
Is the acceleration in that equation angular acceleration?
Oh. Bam. I'll make it better. Okay. Angular acceleration. That's right. And in that one, I messed up twice. Angular acceleration. All right. So without, I think I did like 2 or 3 derivations of the equations. I'm just going to sort of mimic the 2, linear and rotational, right next to each other. Show you how similar they are. So we had linear, And let's just do a couple. Should know these by heart right now. So we have that. That's a linear case. In the rotational case, it is this. But for this, it's only referring to things that rotate. So typically, whenever you are talking about a problem, it'll say, look at this point right here on the rim and follow it along a certain amount. Or look at this part right here on the tire and follow it along. How is this part changing? What is the acceleration? What is the velocity? So using these kinematic equations. All right, we have one example of this. I think I'll start passing out your previous quizzes. So a wheel is initially at rest, and then a constant acceleration is applied. The wheel now has an angular velocity of 10 radians per second and an angular displacement of 5 radians. What is the angular acceleration that was applied to this wheel? So we have those equations. I'll just list them again. And which of these looks like it will help us out the most?
Third one?
Right, yeah, the third one will it just like directly gives us that acceleration that we need. So we know all of the other terms except for acceleration. Yeah, so we'll use the third one. So using that, two alpha change of angular displacement. Angular displacement. Okay. So what is the initial velocity? Initial angular velocity. It says initially at rest, so that always means 0. So it was just sort of sitting there, not moving. We're going to call that the zero, displacement. That's the origin. It's also zero velocity. So, in fact, let me be a bit more specific like that. So that shows us that this is 0 and that is 0. Okay. And I don't want to have to shuffle around large numbers. So I'm just going to solve for the angular acceleration like this. So it's all really nice and clean. So I got to divide over the 2, divide over the angular displacement. Two. So we have 10. Two times 5 radians. Okay. Radians squared over seconds squared. And this is 10 radians squared. So the radians squared cancel. What we're left with is just 10. Let's go down here. 10, I'm going to say revolutions per second. I believe that's what this is. Per second squared. I believe so, yeah. Okay. So, seeing how just this is like the same exact type of problem we've been doing for 2 or 3 months. So, shouldn't be too much of a big step. It's hard trying to wrap your head around where exactly, and the thing is spinning now. It's going to be exactly the same. I'm going to pass out the quiz, and then afterwards I'll go over the quiz for whoever wants to stick around. I will say on the quiz for you guys, I probably could have added a picture or two to make things a bit clearer, so I've handed out some bonuses on the quiz. All right, so I'll see you guys later. See you next time. Yeah.